Hi, this is Codeforces question, Serval and brain power. In this question, we need to return the longest powerful subsequence of S. And T is powerful if there exists string T prime and an integer K greater than or equal to 2, such that T equal T prime plus T prime K times. For example, in this string, the output is 6 because we can take this piece code, then we can take this letter C, then O, then this D. So this is the first T prime and this is the second T prime. Both are equal and of length 2. And so we have K equal 2 because we have 2 copies. Every copy is of length 3, so the total length of this subsequence is 6, and that's why the answer is 6. Now to solve this problem, we need to solve it for different K value. K is greater than or equal to 2. K is the number of copies. Now for K equal 2 and K equal 4, let's take an example for K equal 4. So we have 4 copies. Let's say we have these T primes of length 2. So we have 4 T primes of each one of length 2, and we have K equal 4. So in total we have the length of this subsequence is 8. But also we can take these together to form AB, 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 AB. So we can consider this as first T prime and this is as the second T prime. So we have K equal 2 here. For every T prime, length is 4. So in total we have also 8, the length of this subsequence, and that means we don't need to solve for K equal 4 because it's already covered by K equal 2. Now let's see how can we solve it for K equal 2. Assume we have some string. Now what we need to do is to split this string into 2 parts. Let's say this is the first part and this is the second part. Let's call it this part A and this part B. Now what we need to do is to find the longest common subsequence between these 2 strings. So let's say this part has AB and this part has also AB. That means the longest common subsequence between these 2 parts is AB, AB, and that means the longest subsequence is 2 because we have 2 parts multiplied by this, the longest common subsequence between these 2 parts, which is 2. So we have 4, which is AB, AB. Now remember we split it this way. We can also split it this way. So like this. this is the first part, which is A, and this is the second part, which is B. And also we need to find the longest common subsequence, and if we get better answer, we update our answer. We can split it this way. So this is the first part and this is the second part, so this is A and this is B. And again we need to calculate the longest common subsequence for all possible splitting for the string, and this is what we are doing here. We split the string into two parts, AP, for all the possibilities, and we calculate for everyone the longest common subsequence between the two parts, and we multiply the result by 2, because we have two parts. We need to calculate the length of the whole common subsequence. And for this function, longest common subsequence, take A and B. We use dynamic programming to solve this. So we have here two for loops, and here we have the table, 2D table of size A dot size, B dot size plus 1, and initially all the values are 0, and for every I and j we check if AI equal B j, so we update our value based on the equality. We add +1 to TB of I of j, otherwise the max will be one of these two values. The time complexity for this one is W2, which is small value less than 1, multiplied by the length of the string cube. Because this is small value, we don't need to analyze what is the value of W2. Now this is for k equal to, then we need to check for k equal 3. Again we will do the same thing, but instead of splitting the array into now instead of splitting array into two parts, we will split it into 3 parts. This is part 1, this is part 2, this is part 3, A, B, C, and we need to find the longest common subsequence between these 3 parts, and at the end we multiply the value by 3 here. We need to do this for all possible values of splitting. So for example, we fix A into this part, then we do all the possibilities for B and C, then we increase A to be this section, and we do all splitting between this section for B and C, and so on. So we need for this, the time complexity will be W3 multiplied by S to the power 5. So this is the least common or longest common subsequence for 3 string. It's the same for 2 string, but here we use 3D vectors, and we use 3 for loops, and because we have 3 for loops, the time complexity will be this one, 1 divided by 27 for s square. So why is that? Because as we know, when we split it to when we split the string into three parts, part A, part B, part C, so A plus, or the length of A plus the length of B plus the length of C equal the length of the whole string S, and the dynamic programming code, it will cost the length of A multiplied by the length of B multiplied by the length of C. These are the three for loop, and the maximum for this is when we split the string into three equal parts, A, B, C, and that means A is 1/3 of the length of S, and B is 1/3 of the length of S, and C is 1/3 of the length of S, and this equal 127 of S cube. So this is the max fraction we can get by splitting the string into three parts. If you try different fraction, you will get value less than 1/27, but we are calculating the worst case. Now this is the first part of this W3 S to the power 5. The second part is, as we said, we are going to split the string into three parts. We will do that for all possible splitting, and here in the code we are doing it here. So we get A, then B, then C for all possible values, and the cost of this is half of S square, and that's because if the length of the string, the original string, is S, this is the length of the string. Now splitting this into three parts means that we need to select all the possibilities of picking 2 points on this string. So if we pick this point here and this point here, so the first part of the string is this, the second part is this, and the third part of this. Now, so the problem becomes is how many combinations we can pick these 2 points so that we can form the three section here, and this is the length of S combination of 2. So it's the number of combination when we pick two indexes or two values from S in order to form the three sections, and this equal to the length of S divided by, so let's assume the length of S it is 80, so we have 80 to this equal 80 factorial divided by 80 minus 2 factorial multiplied by 2 factorial, and this equal 80 factorial divided by 78 multiplied by 2 factorial, and this equal 80 multiplied by 79 multiplied by 78 factorial divided by 78 factorial multiplied by 2. So this cancelled, and what remains is almost 8 square, which is the length of s square divided by 2, and this is why here we have half of s square. And so in total the time complexity for this when k equal 3, so the time complexity for this k equal 3 is this number, 1 divided by 54 multiplied by s to the power 5, which is this one. Now we solve for two cases. Now after we solve for k equal 2 and k equal 3, remember also k equal 4 is covered by k equal 2. Now we need to solve for k greater than or equal 5. To do that, we need to split our string into 5 equal parts. Equal means the same length. The last one, it's possible that has less length of the previous 4, but these 4 are of equal length. Now let's take for k greater than or equal 5, let's take an example k equal 5, and assume the length of the longest powerful string is 5. So we have 5 copies. That means the length of t prime is 1. So we can put the longest common subsequence, or the longest powerful subsequence. These are 1, 2, 3, 4, 5, and as you can see here, at least one of the segment contain this copy, because we have k equal 5, we have 5 copies. Now, so at least one segment contains that copy. Assume instead of t equal 1, we have t prime equal 2. The length of the copy is 2, and we have 5 copies. That means the length of the powerful subsequence is 10. 5 multiplied by 2. So let's put these 10 randomly. 3 plus 3, 6, and here we have 3, here we have 1. And as you can see, no matter how you distribute these 10, at least one segment contains this whole copy. Another example is if we take, for example, t prime equal 3, and let's take k equal 6. So 6 multiplied by 3 equal 18. This is the length of the powerful string. Let's distribute this 18 here. So 2 4 4, we have 8, so it remains 10 characters in the last one. And as you can see, no matter how you distribute these characters, the 18, the length of the powerful subsequence, at least one segment can contain the whole T prime, or the whole copy. And that means to solve this problem for k greater than or equal to 5, as we said, first we need to split the string into 5 equal parts, and for every part we need to find all the combination. Let's say here in this part we have AB, here we have CD, here we have A, here we have AB. These parts should be of the same length. Then we have XA, then we have R. So we need to calculate every combination for every part. So for this part we have this A or P or A P. The number of combination in this case is 2 to the power, the length of this segment, 2 minus 1, which is 3. And for this segment we have C, we have D, we have CD. For this we have A, B, AB. For this we have X, A, XA. For this we have R. Now for every combination out of all of these combination, starting from the first segment, we need to assume this is the T prime, this is the copy, and we need to find in the whole string what is the length or how many copies of this pattern A we can find. For example, here we have A, here we have A, here we have A. That means we have 3 copies. So for this combination, which is A, we find 3 copies. The length of the copy is 1, so the powerful is 3, the length of the powerful string. Now we need to try for B. Here we have B, we have 2 copies multiplied by 1, so the solution is better. Then we need to try for AB. Here we have AB, then here we have AB, then that's it. We have 2 copies multiplied by the length of the copy, 2 equal 4, so this is better than 3. Then also we need to try for C. Here we have C, then for D, here we have D only, then for CD we only have this one. Then also we need to try for this pattern. For every pattern we need to find how many copies in the whole string. The time complexity, because we splitted the array, remember, into 5 parts. Let's say we have the length of the string is 80 divided by 5 equals 16, and the number of combination in every for every segment is 2 to the power 16 minus 1, and we have 5 segments. And so the time complexity for k greater than or equal 5 is 5 multiplied by 2 to the power s divided by 5, the length of s divided by 5, which is the length of each segment, multiplied by the length of the whole string, because for every combination we said we need to find how many copies in the whole string, and this is implemented in this part of the code. So first of all, we split the string. This is the first part. So for I equals 0 up to 5, it means 5 parts. For every parts, we will calculate all the combinations, and this is done by first of all getting the substring. The first sub, let's say it's AB. Then we have the indexes map for the letters. So the index of 0 equal A, and index of 1 equal B. This is what we store here. And here we have the number of combination, 2 to the power size of this 2, which is 4, minus 1, because here we start from 1. Then for every possible combination, let's say we have 1, so this is as a mask. 1 represent the binary 1, that means indexes of this bit index is 0. This means that this represent 1. Now if we have 2 representation is 1 0, so this bit set at index 1, and this is for represent B. Now if we have the value 3 in binary is 1 1, and this means we have A, or sorry, this is A and B. So we have this combination. So the string from this is AB, which is this string. So mask is this string calculated, which is the combination, and for every combination we search the whole string for how many copies in the whole string, and if the number of copies is greater than 1, because in the question k must be greater than or equal to 2. If it's 1, we return 0, otherwise we return the number of copies multiplied by the length of the mask.